Hi ladies and gentlemen, so today we're taking a look at graphs of sine and cosine. So to start off, here's a set of 4 warm-up problems just to remind us about how we evaluate these trig functions, specifically pertaining to the unit circle. So sine of pi over 6, if we think back to our unit circle, is 1/2, because it's the y-coordinate at the pi over 6 radian measure. Cosine of pi over 2 is 0. Cosine of pi over 3 is 1/2. And sine of pi over 4 is root 2 over 2. And again, I'm getting that from the unit circle from quadrant 1. Pi over 3 is that first measurement, pi over 4 is the second measurement, and pi over 6 is then that third, giving us the ordered pairs of, let's see here, this one is root 3 over 2, 1/2, root 2 over 2, and root 2 over 2. And then for pi over 6, it's 1/2, root 3 over 2. Right, so that's where I'm getting these answers from, is based upon the radian measure, which is an angle measurement on the unit circle. The x-coordinate at that measurement is cosine, the y-coordinate is sine. So the objective for today is to recognize and graph periodic and trigonometric functions. We're specifically going to be focusing on sine and cosine. But first, let's define what is a periodic function. It's a function that repeats in regular intervals called cycles. The length of a cycle is called its period. So basically, you can copy and paste that cycle over and over and over again, and that'll get your entire graph. So when we're looking at things like graphing sine and cosine, what ends up happening is we graph just part of that unit circle, really, and then it kind of goes on repeat after that, right? So you'll notice that in this part here, this part of the wave is then reflected and just kind of repeated on the other side of the x-axis. And that's because everything in the unit circle is very symmetrical, right? All the points can get reflected across all 4 quadrants. You'll notice that the biggest difference in terms of graphing, when we're graphing these sine and cosine functions, is that our height of these graphs are generally between -1 and +1 for the parent functions. And our x-axis is not numbered in terms of 1, 2, 3, 4, but instead in terms of radians. So pi over 2, pi, 3 pi over 2, 2 pi, so on and so forth. So we have our parent functions for sine and cosine. You'll notice that sine and cosine look very similar, except that sine crosses through the origin, and the parent function cosine crosses the y-axis at 1. So that's the biggest difference between the two of them for their parent functions. Transformation. So just like we had talked about at the very beginning of the school year, everything can be transformed. So we have what's called an amplitude. It's how far stretched the graph is being. So it's like our vertical stretch, right? So if my amplitude is 5, these graphs are going to be 5 times as tall as they normally are. B is the period, and the way we calculate that is by taking 2 pi divided by the absolute value of b. So we'll work through what that is going to look like here. And what that is that's going to tell us how long each cycle is before it goes on repeat again. We have what's called a phase shift, which is going to move your entire wave forward or backwards, and then a vertical shift, which will move the entire wave up or down. So here's our first example problem. We have, let's see, a total of 6 in this lesson. When you're doing these problems, what I recommend doing is getting a graph of sine or the parent function sine and cosine handy. That way there you can reference back to that and apply what these transformations are looking like. So I'll kind of show you on my screen. So what I have is just an enlarged version of the parent function sine. And then I have an enlarged version of the parent function cosine, because this is going to be really helpful for me to refer back to then when I'm creating my new graph. So I recommend having one of those out in front of you, maybe pausing the video and then pressing play to have that as a reference and get that graph somewhere. All right, so let's get started with example 1. We're going to use f of x equals sine of x as a guide, and we're going to graph the function 1/2 times the sine of 1/2 x. Step 1 is to identify the amplitude and period. So that's what we're going to do first. The amplitude, as shown to us on the last slide, is always equal to the absolute value of a, which is what's being multiplied in front of the trig function. So for us, it's what's being multiplied in front of sine, so 1/2. So our amplitude is 1/2. What that means for us is that our graph is going to have a height from the x-axis, from that line of center that divides it in half, of 1/2 of whatever it originally was. And you'll notice if we're looking at the graph of sine here, the parent function sine, it normally goes from -1 to +1. So that means based upon this amplitude being 1/2, my new graph is going to go from -1/2 to +1/2. Then we're going to calculate the period, which is going to tell us how long each cycle is of that wave before it gets put on repeat. Also from the previous slide, the way we calculate period is 2 pi divided by the absolute value of b, and b is what is being multiplied in front of x here inside the trig function, so 1/2 in this case. 2 divided by the absolute value of 1/2 is the same thing as 2 pi times the reciprocal, which would be 2/1. And so we get a length of 4 pi. So what that means for us is normally the length of one cycle of sine that I have highlighted on this side in pink is 2 pi units long, right? Because that's one full circle around the unit circle. And now what's going to happen is it's getting stretched to be 2 times as long, because now it's going to take us all the way out to 4 pi to have a full cycle of that sine wave. So what I'm going to start off by doing is I like to kind of create this floor and ceiling for me when I'm graphing these, and that's going to be based upon my amplitude. So normally this function goes from +1 to -1. But my amplitude is now half of that, so it's going to go from -1/2 to +1/2. So I'm going to have every other tick mark be a half. So this would be 1, -1. Okay, so each tick mark is a half. So I'm going from -1 to 1, and I like to just draw in like a highlighted dashed mark to remind myself that when I go to graph this function, I'm going to be bounded by this amplitude. So none of my points should go above or below these blue dashed lines I have drawn in based upon the amplitude. From here, we're going to go through and draw in the period. And so that's drawing in one cycle of the graph. So what we're going to do for that is, let's see here. I'm going to create a table. So there's a couple of strategies you can use to graph this. And one of the strategies is to create a table. We know that the period of this is 4 pi units long. And sine graphs, based upon the parent function, typically start at 0, 0. And because our graph hasn't been shifted left or right or up or down at all, we're still going to be starting at 0, 0. So I know 0 is going to be the beginning of this sine wave. The end of the sine wave is going to be 4 pi because that's the length of one cycle. And then I'm going to think about what are nice measurements in between that I could also graph. So something like pi and 2 pi and 3 pi. So at 0, I'm still going to be at 0. At pi, when I plug that in, what I'm doing is if we look at this here, go. I'm basically taking this and extending all these points out because it's getting stretched. So at pi, we're going to have a value of 1/2. At 2 pi, if I plug 2 pi into this, 1/2 times 2 pi. So if I'm plugging that into the actual function up here for x, right, the table I've created is I'm plugging these values that I have listed here for x into that function. And you can plug it in, but you have to make sure your calculator is in radians because you're plugging radian values in, right? So if I plug in 2 pi in for x, I'm going to end up getting 0. If I plug 3 pi in for x, I'm going to get -1/2. And if I plug 4 pi in for x, I'm going to get 0 again. So I knew I was going to start with 0 because this is the sine function and it hasn't been moved forward or backwards at all, and that's always a good starting point. I knew to go to 4 pi because that's the length of the period, so I knew that between 0 and 4 pi, that unit's long, I should see a full wave cycle in there. If you look at the graph across, or right here, it only goes to 2 pi, so what I'm going to do is actually modify this slightly to fit the function I have. So I'm going to make it pi instead of pi over 2. And then I'm going to make it 2 pi instead of just pi. And then we'll have 3 pi. And then at the end it'll be 4 pi. So then we will have -pi, -2 pi, -3 pi, and then -4 pi on the other side as well. Now I'm going to go through and graph my points. So I have a point at 0, 0. At pi, I'm at 1/2. At 2 pi, I'm at 0. At 3 pi, I'm at -1/2. And at 4 pi, I'm back at 0. And I connect those, and that's one length of the cycle. And then that's going to go on repeat. So that means I could take this, shift it all backwards until the last point at 4 pi matches up with the first point at 0, 0, and that's going to continue my cycle. So I know that it's going to continue at pi. -pi will be -1/2. At 2 pi will be 0. At -3 pi will be +1/2. And 4 pi is 0. You might be wondering, why didn't you use pi over 2 or 3 pi over 2? And we could have, but those just aren't getting me nice, neat numbers. And because I was going all the way out to 4 pi, there's usually 4 points within one cycle of any sine or cosine function. And so I knew I was going out to 4 pi, so I just divided that into 4s to then get my table. Now, the table is just one way to fill out these graphs. Know that there's other ways to fill out the graphs as well that I'll be showing you next.